The function f of x equals 2x plus 1 defines a map from the closed interval from 1 to 2 to the closed interval from 3 to 5. This can be seen from its graph because when the graph is restricted to the region between x equals 1 and x equals 2, then the y values lie between 3 and 5. In fact, this piece of the graph passes the horizontal line test, which means, as we discussed in a previous video, that the function is 1 to 1. Indeed, for each value in the range, there is a unique input which maps to this value. What this means in turn is that the graph of f actually describes a way of going from the values in the range to inputs in the domain. That is, it actually describes a function, say g, from the range to the domain. One way of thinking about g is that it is the function which reverses or undoes the action of f. Its domain should be the set of outputs of f, that is the range of f, which is the closed interval from 3 to 5. And in addition, its range should be the domain of f, which is the closed interval from 1 to 2. Specifically, in terms of a formula, g is given by the formula g of x equals 1/2 x minus 1/2. Indeed, we can check that this is the correct formula for undoing f, because if we apply g after applying f, then we get back our input x. That is, the composite function g composed with f applied to x is equal to x for each x in the domain of f, that is, in the interval from 1 to 2. In addition, with this particular formula for g, it's easy to see that g does indeed define a map from the interval 3, 5 to 1, 2. Now, the graph of g passes the horizontal line test too, because it's a 1-to-1 function as well, and actually, if we look at the graph closely, we'll realize that it's obtained from the graph of f by a reflection across the line y equals x. In addition, f actually undoes the action of g in the sense that we also have that the composition of f followed by g applied to x equals x as well. Notice that this is the reverse composition that we considered before, which has the important distinction that the input of this new composition, which we've still denoted by x, no longer belongs to the domain of f. Instead, x is now a variable describing elements in the domain of g, which is the interval from 3 to 5. All of these observations are summarized in the following definition of an inverse function. Specifically, if f is a function with domain d and range R, then an inverse for f is a function from R to d which satisfies the property that the composition of g composed with f applied to x equals x for each x in the domain d, and the composition of f followed by g applied to y equals y for each y in the range. It's not too important that we use the variable y in the statement of the second property. Y is just a dummy variable here. But since we already used x as a dummy variable belonging to the domain, we chose to use y as a dummy variable belonging to the range to differentiate between these two sets. Now, suppose we are given an arbitrary function f, and we've computed both its domain and its range. How can we tell when an inverse function exists? Well, one way is to use the horizontal line test. Specifically, if the graph of f passes the horizontal line test, then it will admit an inverse function, as we saw in our first example. What isn't so clear, however, is how to find a specific formula for the desired inverse. For some functions, in fact, there is no nice formula. For example, the exponential function f of x equals 2 to the x defines a map from the set of real numbers to the set of positive real numbers, and this function is 1-to-1 because the graph passes the horizontal line test. It therefore admits an inverse, say g, defined on the set of positive real numbers. In addition, the graph of g is known to be the reflection of the graph of f across the line y equals x. But what is this resulting curve in terms of a formula? Well, the answer is that it has no formula, at least in terms of functions we know so far. So what mathematicians have done is then introduce a new function called log, which describes the function g. In particular, we'll write g of x equals log base 2 of x, where the 2 comes from the fact that 2 is actually the base of f. One way of thinking about this log function is as follows. We say that log base 2 of x equals y if and only if 2 to the y equals x. In this way, some of the properties of the exponential function 2 to the x are then reflected in the properties of this log function. For example, since 2 to the 0 equals 1, we must also have that log base 2 of 1 equals 0. And since 2 to the a times 2 to the b equals 2 to the a plus b, we must also have that log of the product of a and b equals the sum of the log of a plus the log of b. In addition, the property 2 to the a all raised to the b equals 2 to the ab implies that log base 2 of a to the b equals b log base 2 of a. One particular log function is very special, and this is the one corresponding to the special base e, which we called the natural number. For this reason, the corresponding log function is also called the natural logarithm, denoted by ln. This means that ln of x equals log base e of x, where e is the natural number. Now, all of this discussion was to illustrate that we don't always have a readily computable formula for an inverse. But sometimes we do. For example, consider the function at the beginning of the video, f of x equals 2x plus 1. We claim that the inverse of f is g of x equals 1/2 x minus 1/2. But how do we get that formula for g? Well, the method isn't so difficult. It just involves solving for the other variable and the expression of the function. In particular, if we think of the graph of f as the curve y equals 2x plus 1, then this equation defines the variable y as a function of x. But the inverse should express x as a function of y. This means all we have to do to find the inverse is just solve for x in the equality instead. To do this, all we have to do is perform the relevant algebra that isolates x. In this case, we can first subtract 1 from both sides, and then divide by 2. What we then obtain is the expression x equals 1/2 y minus 1/2. That is, x is the function of y described by x of y equals 1/2 y minus 1/2. Here, the variable for the input is y, which is a dummy variable, and can be replaced by any variable we'd like. We could use t to write the function x of t equals 1/2 t minus 1/2, or u to write the function x of u equals 1/2 u minus 1/2. All of these functions are the same as the function g of x equals 1/2 x minus 1/2. They just use different variables for the inputs and outputs. Let's conclude by looking at some trigonometric functions. In particular, let's look at the graph of cosine of x. Now clearly this graph doesn't pass the horizontal line test, so the function cosine of x, as it stands, is not 1-to-1, and therefore it can't be invertible. However, if we restrict the picture enough, the graph does become 1-to-1. In particular, if we restrict our attention to the region between x equals 0 and x equals pi, we see that the curve inside does pass the horizontal line test. What this means then is that when we think of cosine as a function mapping 0 pi to minus 1, 1, it does describe an invertible function. Let's call this restriction f, and let's write g for the inverse, meaning that g should be a map from minus 1, 1 to 0 pi. One way of thinking about cosine is that its input is an angle of rotation, and its output is a horizontal component along the unit circle. It follows that its inverse can be considered as a map going the other way. This means that g should be thought of as a function which takes in a horizontal component in minus 1, 1, and tells us which angle between 0 and pi corresponds to it. For example, the horizontal component of 1 corresponds to the rotation angle of 0. This means that g of 1 equals 0. The horizontal component of 0 corresponds to the rotation angle of pi over 2, which means that g of 0 equals pi over 2. And the horizontal component of 1/2 corresponds to the rotation angle of pi over 3, which means that g of 1/2 equals pi over 3. The function g of x is sometimes written arc cosine of x or even cosine inverse of x. The problem with this notation is that it's slightly unclear what the range of g should be. Remember that we actually chose the range of g by choosing the domain of f. In particular, we restricted our attention to the angles between 0 and pi. But we could have restricted our attention to the angles between pi and 2 pi instead, and we would have obtained another graph of an invertible function. Let's call this alternate restriction f tilde, which we're thinking of as a map defined on the interval from pi to 2 pi. And let's call the corresponding inverse g tilde. Now, g tilde still takes in horizontal components in minus 1-to-1 to produce angles, but now the resulting angles live in the interval from pi to 2 pi. In terms of the unit circle, these angles produce points along the bottom of the circle. For example, the horizontal component of 0 is achieved by the rotation angle of 3 pi over 2, so this means that g tilde of 0 equals 3 pi over 2. And the horizontal component of 1 is achieved by the rotation angle of 2 pi, so this means that g tilde of 1 equals 2 pi. It might be appropriate to call g tilde the function arc cosine as well, since it is a type of inverse for the cosine function, the one where our attention is restricted to the angles between pi and 2 pi. However, in the literature, the standard convention is that arc cos refers to the function whose range is the interval from 0 to pi. On the other hand, the standard convention for sine is that arc sine refers to the function whose range is the interval from minus pi over 2 to pi over 2.